Alright, so we have an electric field of the strength shown there in the problem statement. It's got a location where the strength is, and then there's some particle in the vicinity that has a negative 3 nanocoulomb charge on it. Perhaps we can see it and it's labeled. I don't know why we know that, but we know it. But we'd like to know where that particle is located, given that we know the position of that field strength. So, um, realize that we're dealing with an electric field, positions and charge. So one thing we can count on is that uh, the electric field equation has something to do with it. All right? So we need to realize that at the moment, we have the value of the electric field. We have the value of the charge, but we don't know very much at all about the location. So we don't know R. Okay, in fact, R is going to be, let's switch colors here. R, the vector R, has to be R2 minus R1. We're looking for R1. That's our goal. Where is the particle? It's at R1. We have R2, okay? So we can bank on that piece of information. So that means we need to find a few things. And one of them would be the magnitude of R. So what we should be a bit more careful about is that this is the magnitude of the separation distance squared, which we don't have the separation distance at this point. So let's go ahead and do that. Let's solve this equation for R. So we're going to have K, Q. Let's write that Q a little bit better. There we go. Per the magnitude of E. So I'm going to drop the vector part for now. Well, I need the magnitude of E. Well, we have all its components, so that won't be too hard to calculate. So we could take a pause here and find out what the magnitude of E is. Just going to be the square root of 6480 squared plus minus 8640 squared, which happens to be 1.08 times 10 to the fourth newtons per coulomb. So over here, I'm going to drop all the units just for, we already know that they're the right kind of units. And so this means that when we do all of that number crunching, we're going to get 0.05 meters as the magnitude of this vector. Now realize I have an observation location, which we know that's R2, and then I have some source location that I'd like to know. So it pays to give some attention to the fact that since it's a negative charge at the source location, we know the electric field does that. And the position, the separation distance, would have a unit vector that looks like that. So this tells us that R hat is going to be equal to the opposite of E hat. So the unit vector for the position, the length rather, is going to be the opposite of the unit vector for the electric field. Well, since I know the electric field, and its magnitude, that's going to make it pretty easy to obtain what the unit vector value is. And so when you plug in all the values that we already know, that are on the screen already, we're going to come up with a minus 0.6, 0.8, and 0. So you should be able to do that on your own. Well, just having r hat, we're getting there, but we're not quite there. We still don't know what r is. We know what its magnitude is, but we don't know what it is. Well, by definition, it is the product of its magnitude and its unit vector, which are things we now know. So we put all of that together, and we end up getting the fact that r is a negative 0.03, 0.040 meters. That is the length of this distance between observation and source location. The r vector is also equal to, as we showed before, r2 minus r1, which are position vectors relative to the origin, but r is the difference between those two vectors. And of course that means that r1 is our length vector minus the known position, where the field strength is. So R1, if you plug and chug all of the values and subtract what we've already found, you'll get a negative 0.1, positive 0.10 meters, and we have answered the question.